Hey everyone, we got kind of a skills-based lesson today, so we're not pushing anything new. Still practicing concavity and increasing, decreasing, and all that in the performance task. The next big topic will be curve sketching, so I give you a derivative graph and ask you questions about the original. We'll spend a lot of time connecting derivative graphs to the original function, second derivative graphs, all kinds of stuff. That's fun and challenging. Today is more a skill set of things that I need you to be able to do. Going back to implicitly defined relations. So if you forgot, implicitly defined, which we've done a little bit with, well, we've actually done a decent amount. I've had you make a lot of tangent lines here. Implicitly defined relations are things that look like this. So x squared plus y cubed minus 3y equals 4. All right, so this is implicitly defined because we have y mixed with x. We can't isolate y. So in order to take the derivative, we have to use implicit differentiation. Now, I am going to show you a few new things. I ask you about these things in the discussion. So the first thing I want to do is take the derivative of it, because that's typically the first step, and then we'll use the derivative to answer a few questions that I ask you about when we get into the discussion. All right, so let's take the derivative, power rule. So x squared's derivative is 2x plus derivative of y cubed, no products here. I gave myself an easy problem, good for me. 3y squared. Now, dy dx is what I typically put here. Some of you, well, one of you for sure, looked this up and saw that there's kind of a shorthand. You can start putting y prime if you really want. Y prime means dy dx. So when you see y prime, that means dy dx. And it's the lazy way of doing these problems. So if you start putting y prime instead of dy dx, fine. I do it in BC. I'm scared to do it with you guys in AB because it doesn't tell you what you're taking the derivative with respect to. Since x is the other variable in the problem, it's implied. But it's always important when you start getting into higher calculus what you're taking the derivative with respect to. So I'll use y prime in this example, and I'll probably bounce back to dy dx in the next one. All right, continuing on, derivative of 3y, or negative 3y is negative 3, dy over dx, or oops, and don't mix them up in the middle of the problem, though, that would be bad. So minus 3y prime equals, derivative of 4 is not 4. Derivative of 4 is 0. Okay, another very common mistake people keep making. Derivative of a constant is 0. The slope of a constant function is 0. There is 0 slope. All right, let's get y prime by itself. So I'm going to subtract the 2x over. I'm going to factor out y prime. 3y squared minus 3. Factor out the y prime. I'm leaving the 3 in, and then subtract the negative 2x over. And finally divide. Here I may actually put the dy dx back. Okay, so negative 2x over 3y squared minus 3. Did you everything right there? I hope so. So that's the derivative. We've been doing that. You can plug x and y into that. If I know an xy coordinate, I'd plug both in to find the slope at a specific spot. But that's not what I want to ask. I want to ask you something new with this type of problem. One thing I can ask you to do is find, so first thing I ask you about, find the horizontal tangents. So you can find the horizontal tangents, or the places in this function where you have a relation where you have horizontal tangents. How do you do that? Well, to find horizontal tangents, that's the same as me asking where the derivative, let's do the other notation, where the derivative equals 0, right? Because a horizontal line has a 0 slope, not no slope, 0 slope. So we can set the derivative equal to 0. We have the derivative right here. Let's do it. Negative 2x over 3y squared minus 3. Set this equal to 0. Now, I talked to a few of you about this, and this keeps coming up. When you have a fraction, and you're setting the fraction equal to 0, really you only care about where the numerator equals 0. Because think about this. If I gave you a 0 out of 10 on a quiz, you got 0%. If you got a 0 out of 100 on a quiz, it's worse, but you still got a 0%, okay? It still means 0. 0 over anything is 0. So 0 in the numerator equals 0. So in this case, set the numerator equal to 0, and you get x equals 0. Hooray. We have now found where we have a horizontal tangent. If I wanted to find the y-coordinate associated with that, I could plug back into the original relation. So I could plug 0 into the original and solve for y. But it doesn't work that well in this one because there's cubes and stuff. So we won't do that. But the other question that has started to pop up, it came up on one of the quizzes the other week or so. I can ask you to find the vertical tangents. Find the vertical tangents. How do you do that? Well, horizontal means this way with a slope of 0. A vertical tangent is a moment in time where the slope goes vertical, meaning it goes straight up and down. So what does it mean for a vertical tangent? It doesn't mean where the slope equals 0. It's where the slope is undefined, because a vertical slope is an undefined slope. Super steep, there's no, it's like infinity over 0. You're dividing by 0. There's no run. It's all rise. So when you have a slope that is undefined, that would be a vertical tangent. So how do you figure out where the derivative is undefined? Well, you set the denominator equal to 0. So to do this, it's where the denominator equals 0. That's why we haven't had to typically worry about these in the normal functions, is because we typically don't have denominators that equal 0. We only have if there had been an asymptote in the original problem anyway, and then it wouldn't have even existed there anyway. So typically, in a function, you don't have to find vertical tangents because the function will be undefined there. And you won't have vertical tangents because then it won't be a function, because then it's almost like an overlapping spot. That's not entirely true. There's one type of function when you start getting into certain radicals that messes up a little bit, but we'll not worry about that right now. So we're going to set the denominator equal to 0. So you take the denominator. So I'm going to rewrite my derivative. Set the denominator equal to 0. That's where you're going to have vertical tangents. And solve that. So 3y squared minus 3 equals 0. And let's solve it out. Add 3, divide by 3, square root both sides. So you get two answers, plus or minus 1. 2 spots, and they're in terms of y. That happens in these relations. Sometimes we get answers for x's, sometimes we get answers for y's. If I wanted to find the x's, I could plug 1 back in and get the x's. I'm actually going to do that. So I know it's y equals 1 and y equals -1, because I can actually do this one. So check this out. If I actually wanted the points where I was having vertical tangents, plug them back into the original, way up here. So ready? X squared plus y cubed, but I'm plugging in 1. So 1 minus 3 equals 4. X squared equals, add the 3 over, so 7 minus the 1 is 6. And look what happens in this case. I get x equals plus or minus root 6. So what's going on? I just got 2 more answers. Yeah, I did. That means there are 2 spots in this solution. Oops, backwards. 2 coordinates here, root 6, 1, and negative root 6, 1. There are 2 places we have a vertical tangent, and I'm probably going to get 2 more. So same deal, let's plug -1 into the original relation, x squared plus -1 in this case. Oh wait, is that a cubed? It is, but it doesn't change. -1 cubed is still -1. Plus 3 equals 4. So subtract 3, you get 1. Add 1, you get 2. And finally, we got my other 2. So we have root 2, -1, and negative root 2, -1. We just got 4 points where there are vertical tangents. We had 1 where there's a horizontal, but I only found the x. If I plugged in, I think we'd get 1 or 2 y's. Well, we definitely get 1 y, but we'd probably get more than 1. But I want to look at Desmos and see if we did this correctly. Did we really get 4 spots where there are vertical tangents? Let's see. I'll just be lazy and do this. This is what it looks like. Ready? Vertical tangent means straight up and down. There's 1 when y is 1. Here's the other one when y is 1. Straight up and down vertical. It's where if I zoom super far in, if I go super far in, it looks like the line is, thanks. It looks like the relation goes vertical there. So there are 1, 2, like I just showed you. 1, 2, and look, the other 2, 3, 4. Don't forget, we could do all kinds of fun things like check our answer by making the derivative tangent line thing that I really like. We're not going to do that right now, but you've seen that before. Okay, and then, oh yeah, there's the horizontal tangent at x equals 0. Doesn't look like there were any others. So interesting. Doesn't look like there were any others. There's this one spot. So if I plugged x equals 0, and I would only get one answer because there's no other horizontal tangents. I think this guy just keeps going out this way forever. This guy keeps going out this way forever. Yeah, so that's the only one we got. Interesting. Okay, so that's the first thing, is being able to get out of here. Being able to find vertical tangent locations and horizontal tangent locations. That's what I want you to be able to do. Okay, and then the other thing we are doing in this, we need to be able to find the second derivative in cases like this, where it's implicitly defined. So remember, that looks like this, d squared y over dx squared. They chose this notation so that the squareds don't look like they're in the back, like you're squaring the whole thing. This was just the agreed upon notation for second derivative. All right, so here's where we're at. We have my derivative. Since we already have the derivative, we get to kind of just continue along. All right. I will zoom down there. I'm just rewriting it. So start with your derivative. So yes, you have to find the derivative to find the second derivative. It's just the nature of the game. And we're going to do everything like normal. Do everything like normal. Everything like normal. So here we go. Quotient rule, right? Quotient rule. So low d high. So I'm kind of speeding up a little bit. So this is the second derivative. Low d high. So the low one times the derivative of the high one minus the high one times the derivative of the low one. Ready? 6y, but you took the derivative of a y term. So dy over dx all over the bottom squared. Okay? That's the second derivative with one problem. You cannot have dy dx in your answer. This needs to be in terms of x and y only. So what gives? I only want x and y in my answer. Okay, it doesn't mean they both have to be there. It just means there can only be x's and y's. So I asked you about this in the discussion. How do I get dy dx out of here? Well, look, you know what dy dx equals. It equals this. So yes, you can literally plug this guy right in here. And you now have your incredibly ugly convoluted second derivative, which looks to be 3y squared minus 3 times negative 2. We can do a plus here, plus 12xy times the derivative. All over the bottom squared. Now, there sure is definitely ways to simplify this. You can do a lot of things. We're not going to do that right now. But you can split this into two fractions. Lots of things cancel or combine. We could definitely make this prettier. I'm not spending time on that right now. I just don't want to. All right, so that's the second derivative. And if I look at the derivative graph for a second, or not the original relation, the second derivative works the same way in terms of determining concavity. So like at this point right here, for example, 0 and 2.196. When x is 0 and y is 2.196. This appears to be concave down. It looks concave down. That means if I went to this relation and plugged in 0, comma, I already forgot what it was, 0.2196 or 2.196. So 0, comma, 2.196. If I plugged that in here, I would get a negative second derivative because it's concave down. And you can kind of see that the back term is 0. The front term is, if I plug in 2.196 as my y. I get a big number minus 3 is positive, but times a negative is negative. And I get a negative over a positive, which is a negative second derivative. So I did a lot of that in my head. I might show you on the simpler example in a minute. But second derivative, negative, means concave down. So concavity works the same way in relations. All right. So that's why we have to plug the entire coordinate in. So I asked you about this in the discussion too. I plugged the entire coordinate in. I plugged in 0, it just made this whole back term 0. I plugged in the y, and I got an answer for the second derivative. All right. We're going to do one more example. If you you have the gist of it, you can move on to the homework. Number 3 deals with this, 3 and 4. Here's one more example, though, just to kind of lock in. I'm going to do everything we just did with a much simpler example, just so you can see where you're at. Some people have been doing this ahead of me. So I would try to do all 3 things. I would find horizontal and vertical tangents, and I would find the second derivative. So here we go. Derivative is 4x minus 8y, y prime equals 0. Subtract the 4x over, divide by negative 8y. That's my y prime. Simplify it, I get the derivative is negatives cancel, x over 2y. Pretty nice, pretty straightforward. So horizontal tangents, set the numerator equal to 0. And that's it. So x equals 0 is a horizontal tangent. If I plug 0 back into the original, I could get the y's. It looks like there's going to be 2 of them. So negative 4y squared equals 3. Divide by negative 4. And I get undefined. Interesting. So y equals undefined. We'll take a look at the graph and see what that means in a second. Let's find where the bottom equals 0 to find the vertical tangents. So set the bottom equal to 0, and you get y equals 0 here. So there should be vertical tangents when y is 0. Does this one give me answers? So y equals 0 is a vertical tangent. Let's try it. So 2x squared equals 3. On this one, I get 2 answers. I get x equals plus or minus square root of 3 halves. So what gives? I found a vertical tangent location, 2 of them. But when I tried the horizontal tangent location, I didn't get an answer. Did I do something wrong? Well, Desmos is a great tool for figuring this out. So let's take a look. 2x squared. I mean, you could pause the video and think about why we didn't get an answer. But you're about to see it. Equals 3. Ready? What do you notice about 0? Not in the domain. So we didn't get an answer. We got it. It was kind of like a fake answer. 0 is not in the domain of the original relation. So understanding where the original relation is defined is pretty clutch. But we did get these 2 answers. The vertical tangents are in their right spots at y equals 0, y equals 0, and then the 2 x's. Okay? So being able to check that is always going to be an important thing. This does not give horizontal tangents, but we did get 2 verticals. All right, and finally, let's do the second derivative and call it a day. So we have my derivative. We're going to need that. And we can start from here. So another quotient rule. Typically, it's going to be quotient rule. So the second derivative is low d high, derivative of x is 1, minus high d low. We took the derivative of a y term, all over the bottom squared. Well, y prime can't have it in my answer, so we're going to sub in what y prime really is, and we end up with this, 2y minus 2x times x over 2y all over 2y squared. And yes, lots of simplifying can be done. We're not going to do that right now. And if I wanted to know concavity somewhere, like looking back at the graph, does this appear? It almost looks like it doesn't have concavity. We could test that back and see if we get 0. If we get 0, that means it's linear. So we could pick a point and try it. This point is an interesting one to try. I don't want to do that one right now. Let's just try, well, if we tried this point, you could get it. This one may not be a good example to do this on because there's no concrete numbers, so I don't want to plug in decimals. But you could. We could do the whole positive and negative approach and see what we get. But we're not going to do that in this example. I think I gave you one on the homework to do that. Okay, but those are the major three things: being able to find the second derivative, and using it sometimes. Usually the problems will be crafted so that they lend themselves well to that. And then being able to find horizontal and vertical tangents and making sure that they actually are horizontal and vertical tangents. All right, that's where I'm stopping for now.